Which of the following is required for a reaction to occur? So this is quiz. It's quiz 4. KM theory. Reaction rate. Right here. Kinetic molecular theory is, as I've said before, the molecular level explanation of what particles and reactions do. So one of the things that you want to remember first about this topic, it's a micro level study. Explains well in terms of molecular level behavior. In contrast to this, our work on rate as a function of concentration is a macro level study of kinetic rates. It deals with amounts of material in solution. It doesn't deal with the disappearance of so many particles and things of that nature. Just the concentration issues. That's a macro level. And I say, just as a note, observable changes. Now, when you have to kind of go with that. Observable changes would be changes in concentration, because as you titrate something, as you run the reaction, you have a method over there to detect any changes in concentration. And I showed you one, the vernier, and we'll be using that a lot through the semester. So, macro level studies. So, just want you to understand what the difference is. Okay, now, with using the principles of the kinetic molecular theory, we have what is called reaction factors. And I gave you a very simple acronym. What was that? CENT. C-E-N-T. Okay? C-E-N-T. Do not get this confused with the rate factors. These are reaction factors. The rate factors were the can't see issue. You change one of those components or factors in an experiment, the rate will change. If you change one of these or leave one out, the reaction will not happen. That's the difference. You must have a kinetic concentration, or a proper kinetic concentration of reactants. Meaning that the reacting particles must be able to find one another in order to react. As the reaction proceeds, products are formed and there are fewer and fewer reactants. And they become harder to find each other. And therefore, over time, the reaction rates will decrease. That's the decay curve, because we have fewer and fewer particles being able to find one another. It has to enjoy effective collisions. Collision, C-O-L-L-I. Well, anyway, effective collisions, that has to do with orientation of molecules on collision. I think this is somewhat self-explanatory. I'm sure it's easy to visualize. This would be more effective than this in terms of the particles having a chance to bond. Naturally reacting substances must be used. That's a nature issue. Naturally reacting reagents must be certainly in place. Of course, that is dependent on the objective of your experiment and what you're trying to do. You'll know that from a theoretical foundation ahead of time. And it must have a temperature such that it can push the intrinsic energy or the positional energy of the reactants up to an activation point or an activation energy. So the temperature to give activation energy. As you raise the temperature, you're putting energy into the particles. The particle levels are going up toward that activation point. And I'll bring that in shortly. All of the examples in here are reaction factors.
Did we go over last time what proper?
Again. Okay. Okay, number 2. Okay, basic Arrhenius equation is given here. K equals A E to the minus delta E over RT. Now this is just kind of an interpretive question. As the activation energy increases, basically is what they're asking you. How does it affect the rate constant? If the activation energy increases, the rate decreases. It's an inverse relationship. If you consider a graph, transition state graph, say like this one, well, this is your activation point, EA. However, if you throw into that mix some type of catalyst that you want to inhibit the reaction, you might push the activation energy up here to point number 2. Like that. The way I like to remember this in a generic way is kind of like running across a mountain. The higher the hill, the harder it is to get over. And it's going to take you longer to get across the hill. So this would have a K value, so we call it K value for EA2, less than K1. Now, rate constants are proportionality constants in the rate laws and have a variety of units depending on the reaction you're running. You have to go back and look at that. I don't have time to go back through that. But the numerical value of the rate constant when compared to the numerical value of another rate constant, the larger rate constant, K value, is the faster reaction. K2 would be less, larger K value, so K1 would be the larger value. I need to. That's potential energy, and this is reaction progress. Okay, as you go through the reaction. Now, there are catalysts whereby you put the catalyst into the solution, it will speed it up. There are accelerators, as they call them. They function to lower the reaction rate. So this being, say, K3, making a mess, sorry. If this is K3, then 1 would be less than K3. And so this would have the fastest of the three reactions illustrated. It's the same reaction, except you put something into the mix that either raises the activation energy or something that kind of pushes it down, a lower hill, flat line, or whatever. Everybody kind of understand this? Catalysts change the activation energy. Please note that. I have that on the test coming up there. Catalysts function to change the activation energy. And most of you know the definition of a catalyst. It functions to change the rate of reaction. Yes? Catalysts either speed them up or slow them down. When you throw in a catalyst, it's going to speed it up if it's one that will lower the activation energy. If you throw in a catalyst that slows the reaction down, it's called a retarding agent or decelerating catalyst, and will function to raise the activation energy so that it's harder for the reactants to get up to the activation energy, and the reaction is a lot slower. Try to run over a steep U, start pedaling across on a bicycle over the top of a hill. It's very tall, high. It'll take you longer to get over that hill than one that's short to the same point. Okay, does that make sense, guys? Now, the Arrhenius equation is the classic equation for kinetic rates at the molecular level. It's a probability thing. And out of this comes the Arrhenius equation that we talked about. And you can derive it out of this. But what I want you to see is this is a speedometer. And it's attached to a negative exponent. This is actually the activation energy, EA. Negative exponents be reciprocal. And reciprocal of a reciprocal will still be inversely related to K. So if you want a higher number here, you would have to have a lower number in the delta E position. If you want a lower number in the K position, you would have to have a larger delta E in there. So this equation ultimately says this in general. Okay. Okay. Any questions on that? Okay. Which of the following is an exothermic reaction? It's one that liberates energy from the system, and the system energy components are below the starting reactant components. I'll give you both of them. If we start here, well, I'll start here. Can you give me some room? We see that the energy level, of the products of the reaction is below the energy level of the reactant. This is classified as a negative delta H is of reaction. That's the same thing as saying energy. You will understand why I use delta H when we get to thermodynamics later in the semester. But delta H is what we call a closed system energy change. Long story. So there to there is less than 0. And so we classify this one as an exothermic reaction because the E of products, that's your positional energy or internal energy of the products, is less than the internal energy of the reactants. There we go. They appear magically, so you don't have to see me drawing pictures all the time. So that's an advantage. So in this case, delta H of the reaction is greater than 0, and that the product side is above the starting position, and this is an endothermic. E of the products is greater than E of the reactants. One issue that I spend more time on when we get to thermodynamics than I do now is the definition of endothermic and exothermic are always relative to the system undergoing reaction, not the surroundings. And many people, many students struggle with that idea. So when we talk about endothermic and exothermic, we might look at it, say, like there. Here is your reaction, right there. And over here you have surroundings. Partition between the two. The reaction is always the system, or the object of interest, and the surroundings everything else. If the reaction is exothermic, then energy is moving away from the reaction. Into whatever the surroundings are. Now here's what I'm trying to say to you. When we use the terms endothermic and exothermic generically, there's no relative indication, but in your mind you should understand, in the world of science, it refers to the reaction. Because if you look at the surroundings, it's endothermic to the surroundings. And so we can't call this an endothermic process. It's endothermic to the surroundings. But we're interested always in the change of energy at the reaction level. And you can turn that around if you wished and take into account, say, a gain of energy is exothermic, though, now to the surroundings, but endothermic to the system. So I wanted to make that point so that you won't make the mistake in the future of trying to draw conclusions about reactions and call them endothermic when they're actually exothermic and vice versa. Based on the data that you receive has to be interpreted relative to that system. Sometimes the graphs show an increase in temperature. Well, that's surroundings increasing in temperature. And where did the temperature increase come from? Or the energy to increase temperature came from the system. And so you have to say the system is losing energy, exothermic. B choice. In number 4, the activation energy for the forward reaction is 20 kilojoules, and the activation energy for the reverse is 200 kilojoules. Is the reaction endothermic or exothermic? And what is the net energy change of reaction? Well, looking at the data here, 20 kilojoules is plus. So that means it's an endothermic in that. But the reverse reaction over here, if you see my diagram, is 200. So when I draw my transition state diagram, I have to show it as an exothermic reaction. Okay? Listen, there are 3 primary terms you've got to be aware of here. Activation energy of the forward reaction, activation energy of the reverse reaction, and heat of reaction. The activation energy for the forward reaction is right here. I'll put an F forward. The activation energy for the reverse is delta E reverse. In both cases, the energy they're talking about requires to be put in. It's always endothermic. If I want to reverse the reaction, I have to put in enough energy to get it back up here to the activation point. Or if I'm talking about a left to right or forward reaction, I have to put in enough energy to get to here. Well, the problem gave us 2 pieces of information. That's 200 kilojoules that I'd have to put back in to get it back over the hump here. And this one was 20 kilojoules. The only other issue in this is the heat of reaction, which is the differential between the beginning E initial, EI, and final energy of the system. This is the system energy before it starts. You haven't got any products. Then when reaction reaches equilibrium, this is your energy. So we've gone from here through all of this here, and since, let's see, this is reaction progress. Okay, and EP. when we want to calculate the change in energy, we calculate E final minus E initial if E final is less than E initial, then delta E is less than 0 or negative. And that indicates an exothermic reaction. So the heat of reaction is delta E, I'm going to call it delta E of reaction. Delta H and delta E are the same thing for right now. A reaction. Now, when we talk about determining these, even though this is exothermic and it's supposed to come out negative, what they're asking you to do in here is compare the distances between the two on the left side of the activation point and the distance on the right. See how they're equal? Well, the red lines are equal. Well, the red line on the reactant side is the sum of E final plus delta H of reaction, and that's going to equal the delta E of reverse, or heat of E. I'll be consistent of reaction. See, final is above the initial. No, that's wrong there. That's F for forward. Initial activation energy from here to here, okay, is 20 plus activation energy, reaction, sorry, equals 200. I'm trying to rush. So this is delta E of reaction is now 200 minus 20 in kilojoules, which is 180 kilojoules. Exothermic. Looks like D choice for those keeping score. I hope you're taking some notes because this is your review for the exam. But the last lecture is not going to be a review for the exam. It's going to go right up to it, and then next class you'll have your exam.
So it's exothermic even though it's not negative?
Sorry. That's what you're asking. Same issue. In this, you have to compare the left side relative to the activation point to the right side. In this scenario, the delta E for the forward reaction equals delta E for the reverse plus delta E for the reaction. Now, if they're asking you to get the delta E of the reaction, you have to use this relationship solving for delta E reverse and delta E forward minus delta E or E reverse, E forward, delta E reverse is 200 minus 20 kilojoules or 180 kilojoules for this part right here. Because you got 180 plus 20 gives you this. Same issue. This problem requires that you compare the lengths of those two sides. You know, this equal that, or in the above case, this and this equal that. If the reaction inherently is exothermic, fine, assign a negative sign to it. If it's inherently endothermic, whatever this is right here, assign the endothermic. So in the actual reaction, reverse reaction is 100, so you would have an endothermic reaction, delta E reaction, equal to plus 180 kilojoules. However, let me start. back down. In this one right here, even though the unknown was this, you calculated the heat of reaction because it's between here and here. And 180 plus 20 gives you the other side. Well, looking at the diagram, it is exothermic. And so if you had to report the change in energy of the reaction, you would report it as a negative 180 kilojoules. That's the definition of exothermic reaction. But to solve a problem like this and get that specific distance from the axis to the position of the reactants, man, this is just generic, just what we've been talking about. If a reaction gains energy, it's said to be endothermic or exothermic? Endothermic. If the reaction system gains energy, it's endothermic. And the product side of the positional energy would be above the reactant side. This is what we've been talking about the last few minutes. Okay, so the system gains energy. When a problem comes to you in this context, it'll give you a heat of reaction is plus 20. Okay, so you know that if it's plus, to draw the graph, the transition state graph, with the products above the reactants. Because it'll give you what the reaction is. Given delta E of the reaction equals 20 kilojoules. If the problem gives you delta E of reaction is equal to minus 20 kilojoules, basically you have to draw this. Because this is going to be 20 heat of reaction. Up here 20 is above the beginning point. So this one is endothermic per the question and winds up above the reactant products, and that's a choice in that. This is I'm going to put this at the end of the video. It'll be on there. 4 types of KM theory problems. Exam. Transition state. Curves. And this is what we've just talked about, comparing the left side and the right side. You have to know, to work these kind of problems, you have to know from the problem and looking at the data whether or not the curve is an endothermic or exothermic curve. You draw it and put it in the data. You have to know the terms, yes? The 3 terms are delta E forward, delta E reverse, and delta E of reaction. You just have to know where to put those. After you've made a decision whether it's endothermic or exothermic, draw your graph, put those in. Look at the left side and the right side and see what needs to be calculated. Left side equals right side, solve for the unknown. That's an easy problem to get, but it can confuse because we're so used to looking at the numbers associated with exothermic, endothermic as being positive or negative. Well, in this case, that's not the issue. Positive and negative is not the issue. Is what number do I put in to fill the gap? That's all it is. You will have simply to draw and label charts for endo and exo reactions. So data we get, and you just draw it out and or make decisions about what the diagram is actually meaning. And you'll have one on the Arrhenius equation. I didn't give that on the quiz because it certainly takes a lot of time and it's work intensive to get through it. But please practice the Arrhenius, solving problems with the Arrhenius equation. We did one the other day. And these are used to calculate delta E. E to a rate constant. But you have to give in two or three. You have to have two reference data points: K value 1 and a temperature 1. And the problem will ask you, well, what's the K value at temperature 2? Something like that. You can also ask, what's temperature would double the rate reaction? And so you would be calculating temperature out of this now. I'll make it easy on you. The one I give is find activation energy. And I'll give you all those stuff.